Hello there, Wednesday, April 14th, 2021. In our lecture for today, we're going to be talking about the nature of the phase transitions between the normal and superconducting state in the type 2 superconductors. So last lecture, what we did was we calculated, roughly speaking, the surface tension of the normal superconducting boundary, and we calculated it in two different limits. In one limit, we calculated when the correlation length was much larger than the penetration depth. And in that limit, what we saw was that there was a small region where of order psi, where the superconductor did not gain condensation energy, did not get the full benefit of having a condensate in a region of order psi. And so what that means is that the energy was higher than it otherwise would have been. And so we've discovered then that the energy of a domain wall between normal and superconducting state was given by the correlation length times the cross-sectional area of the superconductor times the difference between the free energy of the superconducting and normal states, which we know is the thermodynamic critical field hc squared over 8 pi. In the opposite limit, when the correlation length was smaller than the penetration depth, then a similar thing happened, but in this particular case, you've got a region where you've lowered the energy of the system by forming a condensate, but you haven't had to pay the price of expelling the magnetic field. And therefore, as a result, the energy is in fact lower than it would otherwise be. And so you can get a surface tension which is either positive or negative. So now let's explore the consequences of that. And let's ask the following question. What happens when we take a superconductor, vary the external magnetic field or vary the temperature, and what do we expect to happen as we undergo the transition to the superconducting state? So this section we're going to call nucleation of superconductivity in bulk. So what we've seen then is that the energy of a domain wall between normal and superconducting states can be either positive or negative, depending on whether psi is larger than or smaller than lambda. In other words, whether the kappa parameter, which is lambda over psi, is much less than 1 or much greater than 1. So that's what we've deduced so far. So let's have a look then at the phase diagram as we've already seen it. So here we go. So here is the temperature H field. Here is the thermodynamic critical field. So this is the superconducting state. This is the normal state. This transition across this boundary is a first order transition. And this line defines Hc of t. And and so we can ask what happens then as we vary the magnetic field and we go through the thermodynamic critical field. So let's imagine, if you will, that we ask what happens if we draw this line along here. And I think that color's too dim, so I'm going to make it a bit brighter. There we go. All right, so I want to ask what happens as you start off at, say, this point here, and then go down in field as at fixed temperature below Tc. So there's Tc over there. So why don't we do this? Why don't we plot the magnitude of the order parameter psi as we go through this transition? And so what's going to happen is not very surprising. We get to the thermodynamic critical field Hc of T. Above that, the order parameter is 0. Below that, it jumps discontinuously to whatever value it should be. And this value here is what we've called psi naught before. And so that's simply what happens for fixed T less than critical temperature. Okay, so this is a first order transition, and so let's just basically review the kinetics of first order phase transitions. So let's talk about the kinetics. So the most important thing to know about first order phase transitions is that they occur when there is a nucleation barrier between the states. So in a first order transition, there's a barrier separating the metastable state from the global minimum state. And I'm only going to give you a very crude sort of mean field physical picture of what I mean by that. So if we were to draw this like so this might be the order parameter, this might be the free energy, and typically what happens is you're in a state that is initially this one. So let's say this is psi equals 0, this is psi is psi naught, and so this is where you've started off your system, and there's some free energy barrier that takes you let's call it delta E between these states. And so what's happened is as I've changed the magnetic field, as I've changed the temperature, what's happened is that the state over here, the global minimum, has goes below the metastable minimum, as H or T is varied, and psi jumps discontinuously. And why does it jump discontinuously? Well, let's have a look here over here. So it starts off at being psi is equal to 0, and the minute that this state here becomes lower, that this state becomes lower than this state, then the order parameter jumps from here to this value, and that's a discontinuous jump. And that's why we call it a first order transition, because there's a discontinuity and there's that discontinuity. Discontinuity. There we go. Okay, so that's the equilibrium thermodynamics of it, that there's a jump there. How does it actually take place? So when we talk about the kinetics, what we're asking is how quickly does it occur? And actually a subsidiary question, which it's not really disconnected from, is not just that it's we should ask how quickly does it take place, but how spatially does it take place? So the basic idea then is that you have to create a nucleation droplet in the background of the metastable state. So let's draw a picture of that. So here's our physical system. And we're going to assume that most of the system is in the metastable state. So I've lowered the temperature. What was originally a global state, is a global minimum state, is now a higher energy metastable state. And what's going to happen is in the middle of the system, there's going to be some kind of droplet of the global minimum state. So let's draw that droplet as having a radius r, and let's annotate it. So this is a droplet of the global minimum. Now, how did this picture arise like this? Well, what's happening is that the system is in a metastable state. There are thermal fluctuations happening all over, and every now and then, maybe very rarely, you get enough fluctuation that you create a little bit of a droplet of the metastable state in the system. And so if we go over to our diagram on the left over here, what that corresponds to is that the system is sort of trying to making fluctuations and trying to get over this barrier. So what it wants to do is gradually go over this barrier like this. But typically what happens is it'll do some random walk in this barrier, get up to here, look like it's about to go over, and then it will start to come back down again. And so it's kind of oscillating back and forth over here, and only very rarely is it going to be able to get over that energy barrier. So we could say that this is very very rare fluctuation. That gets you over the this energy barrier. So let's see how difficult that has to be. So this is a droplet of the global minimum state in our present situation. In the present example, what that means is a droplet of superconductivity in the metastable state, which is the normal state. So let's ask ourselves what the free energy difference is, or what is the free energy cost of this droplet. So the free energy of this droplet is going to be the following. Well, first of all, it does have a lower free energy in the bulk because it's the global minimum. So let us say that that it has an energy. It's a circle. It's a sphere. So it's 4/3 pi r cubed. That's the volume times the energy gain per unit volume. We're going to call that epsilon. So this epsilon then is going to be the energy gain from being in the superconducting state. Condensation energy which is, as we know, hc squared over 8 pi. But then there's also a domain wall here, and that domain wall also costs energy. So there's a plus that comes in here, and that comes from the surface. Well, if it was planar, it would be a domain wall. It's just the surface area of the sphere. So this is 4 pi r squared times the surface tension. And that surface tension is the thing that we calculated last lecture. So that's the surface tension. That's the thing that we called the E wall. Well, this whole thing is the energy of the wall in the spherical case. So this is the energy of the wall per unit area. But you understand what I mean. So now that we know this, then we can plot what this looks like. So here is the free energy of the droplet as a function of radius, and as you can see, for small r it goes up as a quadratic. For large r it goes down as a cubic. So it's going to sort of do something like this. And this maximum value here is the critical radius. And so what basically happens if we go to our picture that we had over here of the system going over the free energy barrier. So what's happening is you're making a fluctuation up here, then it's going back down, then it's going back up, then it's going all the way back down again, then it's going back up, and so on and so forth. And only when it gets over this barrier, then can it, by growing, expand and fill the system. So here the droplet never grows. And then here the droplet does grow. And that leads to the transition to take place. Because the whole system becomes in the superconducting state. And if you want to know how long that takes, what people typically say is the sort of usual model of this is that the fluctuations occur at a rate 1 over tau is given by omega naught e to the minus f of r c over kt. And this is a highly non-trivial formula because, of course, we have t here as if this were an equilibrium. But this is the lifetime of a non-equilibrium state, namely the metastable state. So this is this omega naught is sometimes called an attempt frequency. Now, so this is the case. So all of this is fine, and this applies when sigma is positive. And that means, in other words, that lambda is much smaller than the correlation length. So that's what we're going to end up calling a type 1 superconductor. So for type 2 superconductors, actually what happens is that lambda is much larger than psi, and in fact, we'll see this, kappa has to be bigger than 1/√2. So in this case, then there's no nucleation barrier. So what happens? And the answer is that the system goes into the superconducting state through a completely different mechanism. And in fact, transition occurs at a higher temperature, sorry, a higher field, which is greater than HC, and is a second order transition, or continuous transition. Okay, so how are we going to do this? So here's the strategy that we're going to follow. So we're going to start off. With a temperature less than Tc. Then we're going to solve the Ginzburg-Landau equations. In a magnetic field. And solve for psi as h is reduced from infinity. And what we're going to be looking for is we're going to already know that there's going to be a second order phase transition because there isn't because the nucleation barrier has disappeared. So we suspect there's going to be a second order phase transition. So what we're going to look for, so we're going to look for a second order transition. And the characteristic of a second order transition is that the order parameter doesn't change discontinuously, but changes continuously. So that's why we call this a continuous transition or second order transition. The real thing that matters is whether or not the order parameter changes continuously. So let's sort of draw the cartoon picture of the phase diagram. So here we are in the temperature external magnetic field plane, like so. We have our thermodynamic critical field like so. Well, actually, I'm not going to draw the thermodynamic critical field. We're going to draw the HC2 line. So let's call this HC2 of T. So we're going to find such a value, and the idea is that across this line here, this is a second order transition, and this value here would be HC2, that would be TC, and this is HC2 of T. Okay, so that's the picture. So what we expect to correspondingly happen to the order parameter is now I'm varying external magnetic field. I'm changing the magnitude. I'm changing external field. I'm keeping the temperature fixed. So this is exactly like what we had before. And now what's going to happen is that as I get to HC2, the order parameter is going to go from 0 up in some way like this. And so this is in complete contrast with what we saw over here on the left blackboard, where there's a jump. So this is the picture that we are expecting. So let's now go ahead and do the calculation that justifies this. Now, the point about the calculation is that because we are looking for a second order transition or continuous transition, then we know that in the vicinity of it, the absolute value of psi is going to be much less than 1. And so we can linearize the Ginzburg-Landau equations. So let's write down the Ginzburg-Landau equations. So here we go. So this is in this crazy system of units, minus h bar squared of 4m grad minus 2I e over h bar c a. That operator squared acting on psi plus alpha psi plus beta psi, absolute value of psi squared is equal to 0. So that's the Ginzburg-Landau equations. And because we're going to be working in the regime above the transition, we are going to psi is going to be small, and so we're going to neglect this term here for that reason. So once that term goes away, then we're left with a much simpler equation, and one that we perhaps might even recognize. So this gives us minus h bar squared over 2, I'm going to write it like this, 2m star grad minus I e star over h bar c, oops, times a. This operator squared acting on psi is equal to e psi. So I'm going to write it like this, where m star is equal to 2m, e star is equal to 2e, and when I write down e, what I mean by e is minus alpha. So all I've done is basically throw away this term up here, and then take this term over to the right-hand side and call that like that, call that minus e. Now the reason I've done it like this is because this once I've got this equation, this might be familiar to you. This is the equation for a charged particle in an external magnetic field. So this is the Schrödinger equation. or the time-independent Schrödinger equation for a charged particle in a magnetic field. And this problem was solved by Landau in 1930. And the solutions have got two quantum numbers. So what we want to do is solve that equation and look for the eigenvalues. So that the eigenvalues are characterized by two numbers. So we have E as a function of n and kz, and kz is the momenta in the direction of the magnetic field. And let me write down the formula and then just show you the geometry. So before I lose my place, this is h bar squared kz squared over twice the mass of the particle plus n plus 1/2 E star h bar h over m star c. So those are the eigenvalues, the energy eigenvalues, and in this expression here, h is the curl of A as usual, and we've assumed that is of magnitude h going up the z-axis like so. So we have a system of coordinates like so, and these are just the energy eigenvalues, and they're plane waves in the z direction, and they are orbits, cyclotron orbits in the xy plane, and so that's why you have a kind of harmonic oscillator type of formula in the xy plane for the energy, and then it's just a free particle translational motion in the z direction. Okay, so that's the energy. Now, what we're trying to figure out is the first magnetic field where the system first has a solution. So how do we use this in our particular problem? So we want to, for our problem, what we want to obtain we want to find when there is a non-trivial solution, and what we want to do is which corresponds to the largest value of H, the external field, for which psi is non-zero. So that's what we want to do. So let's see what that means. So the smallest value of E is we set kz equal to 0 and n is equal to 0, and so we just get 1/2 E star h bar h over m star c. So what we need then is to have a solution. So we know that E is equal to minus alpha, which is the same thing as the absolute value of alpha. So we can say that, so I'm going to write this down here, E is minus alpha, which is the same as the absolute value of alpha. So now I can write down that the absolute value of alpha is equal to h bar squared kz squared over 2 m star plus n plus a half e star h bar h over m star c. Okay, so what is the largest value of h for which this occurs? So imagine now that we've set alpha. We want to find what is the largest value of h. So that to get the largest value of h, we want to set n and kz equal to 0. So to get the largest value, we want to make kz and n both be equal to 0. And then what is the value that you get? So now I have that absolute value of alpha is equal to 1/2 e star h bar h over m star c. And so turning that around, what I get is that largest value of h, which is what we're going to call hc2 of t, is then just given by 2 m star c over e star h bar times alpha. Okay, so let me just go through the logic again. So we have this relationship over here, which comes from solving the Schrödinger equation. We can translate that relationship using these correspondences between the time-independent Ginsburg-Landau equation and the time-independent Schrödinger equation. And so that gives us this equation over here, which has to be satisfied. So you tell me what t is, has to be a t less than tc. Then I want to find what is the largest value of h that satisfies the equation over here on the right-hand side. And so I have to set k and z and n equal to 0. And then the formula that I've written down at the bottom here tells me for that value of t, what is the largest value of h for which I can get a solution of this equation. And that largest value of h is by definition what we mean by hc2, because this is the largest value of h for which I have superconducting solutions. Okay, so let's then take this formula and manipulate it. So this form is fine, but not very useful. So we can express this in terms of measurable quantities, which is always what we want to do in Ginsburg-Landau theory. So how do we do that? Well, remember before we had calculated that the correlation length was given by h bar squared over 4m alpha of t. So that was one of the things that we worked out last lecture. And so that means that hc2 I can write then in the following way. It's 2mc over e times h over 2 pi. So I'm writing it in a rather perverse way like that, times alpha of t. And so I can then write this as, and of course, inconveniently I have to go over the page. I can then write this as 2mc e over h over 2 pi, okay, I've written it again, times h bar squared over 4m psi of t squared, so replacing alpha by the correlation length squared, and that gives me hc over 2e, and then 1 over 2 pi times the correlation length squared. So I've written it in this way, and this is hc2 is related to the correlation length in this way, and this thing over here is the thing that I had mentioned to you in the introduction. This is the Fluxoid quantum. And this has the value about 2.07 times 10 to the minus 7 Gauss centimeter squared. So the next thing we need to ask is, so now we found hc2, but we now need to know whether or not that is above or below the thermodynamic critical field. So here's our phase diagram. Right, so we've now got two curves in this thing. We've got a curve that looks like this. Let me call this one hc2. That's the one that we've just calculated. And then we have another curve, which is the one that we've calculated before. So let me draw that over here like this. So this is hc of t, or it could be out here. We don't really know which one it is. So if it were this case, if it was this, then you would see the first order transition before you got to the second order one. As h is reduced from infinity. So you're imagining that you're coming down from infinity, and you ask yourself, what is the transition that I first see as I lower the external magnetic field? And if it's the HC line, then you see a first order transition. If it's the HC2 line, then you see a second order transition. And so this one is, if yes, then the first order transition before you reach HC2. If it is this one, then the HC2 transition occurs first as you lower the field from an infinite value. So let's see if we can calculate whether it's above or below the thermodynamic critical field. So next. Okay, so that's what we're going to do. So let's do the calculation. So let's remind ourselves what HC was. So earlier on, I showed you, last lecture, I showed you that HC is equal to 4 pi over beta to the 1/2 times the absolute value of alpha. Now, the other thing is, we know that the electromagnetic penetration depth, I also derived that for you last lecture, that was given by this formula, mc squared beta over 8 pi e squared absolute value of alpha. All of that to the 1/2. So that's the penetration depth. So now this quantity kappa, so what this means is that if I want to compute kappa squared, so kappa was, if you remember, the ratio of lambda over xi, so this is lambda squared over xi squared. I can take these two formulae and divide them. So then kappa squared is equal to 4m squared c squared beta over 8 pi e squared h bar squared. All the temperature dependence has cancelled out. So then now go back to formula for HC2. So remember, HC2 was given by this formula over here in terms of alpha. So I can use this formula to write HC2 is equal to 2mc e over h bar times the square root of beta over 4 pi, and this is equal to 2. All I'm doing here is manipulations. That there's nothing fundamentally interesting about them, but this is just the algebra for getting the results. It's a bit fiddly. Nothing I can do about that, I'm afraid. So HC2 in terms of HC is multiplied by those constants. And now if I look at those constants, I can identify them as being kappa. And so this means that HC2 is equal to square root of 2 times kappa times HC of t. Okay, so now what we have to do is we have to use our reasoning before to see whether HC2 is greater than or less than HC. So we can see that HC2 is going to be greater than or less than HC depending on the sign, not the sign, the magnitude of this square root of 2 over kappa. So what we learn from this is that if kappa is greater than 1 over the square root of 2, then HC2 is greater than HC, and so that means that we get a continuous transition. On the other hand, if kappa is less than 1 over the square root of 2, then HC2 is less than HC, and that means we have a first order transition. And so whether or not we have a first order, a type 1 or a type 2 superconductor, depends on the value of kappa with respect to 1 over the square root of 2. And so this type, where kappa is small, that's called a type 1 superconductor. And when it's larger, it's called a type 2. And when it's larger, we know that that means that we have a negative surface energy. So up to now, we had really just said it just depends on whether lambda is much larger than xi or xi is much greater than lambda. Now we can be a lot more precise. Now we can see that the actual criterion is 1 over the square root of 2. Okay, so I'm going to skip over some of the comments that I make in the notes. I'll let you read them. So I do want to talk about what the significance of this is in terms of vortices. So I want to make some comments. Okay, so all that I've done so far is show you where the transition occurs. We haven't yet discussed what happens when you're below the transition. So so far, we worked only with the linearized equations. But as we go into the superconducting state, we need to include the nonlinearities. So what that means is that we now need to solve the nonlinear Ginzburg-Landau equations, and this was done first of all by Abrikosov in 1956, and what he showed is that what you get is a periodic array of flux tubes. And this is the result that you will derive in the homework. And you'll derive this using gauge invariance. In a rather elegant way, so much different from the way that Abrikosov did this. And what is the physical interpretation? Now, I've mentioned this before, but I think it bears repeating. So the physical interpretation is that it is that the surface tension or surface energy is negative, and so that means it is favorable to create as much surface as you can between the normal and the superconducting regions. And what happens is you get these vortex cores. So they're normal inside, and then they're superconducting outside, and magnetic flux is going through. I don't know how to draw this. This is meant to show you magnetic flux going through the vortex core. So and then away from it, it decays exponentially to zero. So and it falls off with a length scale given by the penetration depth. So that's what we see, and as I told you before, the flux through the tube is in units of phi 0, and all of this is exactly like what happens in a rotating superfluid. where the velocity field decays like 1 over r away from the core. In the superconductor, the magnetic field decays exponentially away, and that's that really that difference of the power law decay and the exponential decay is because one of them has a gauge symmetry and the other one does not. So let's talk about the what I want to do is I want to talk about the transition between the Abrikosov vortex phase and the Meissner phase. So this is comment number 1 that we've made. So now let's make comment number 2. What happens as we go further below HC2 at some fixed temperature T. So what I want to show you is that there is a phase transition to the Meissner phase, and I want to explain to you how that happens. So let's see. Let's argue how that happens. So we're going to assume that that we're going to fix H to be fixed at some H which is less than HC2 T. And now what we're going to do is reduce the temperature. So let me draw the phase diagram that I have in my mind. So here we are, this is temperature, this is TC, this is H. And so what we've talked about just up to now is this line HC2. Like so. So this is a second order transition. This is HC2 of T, like so. This is the normal state. Everything under here is superconducting, of course. And so now what I want to do is choose an H. So this H, which is less than HC2, and now ask what happens as we start reducing the temperature and going in this direction. Okay, so that's where we're going in the magnetic field plane. So as we reduce the temperature, then the penetration depth gets reduced. Now, remember that in the negative surface energy in a type 2 superconductor was negative by an amount of order lambda. So remember over here, let's just go back a couple of blackboards. Where are we? Yeah. Okay, so remember here, the energy that we have when we have a negative surface tension is governed by the value of lambda. So now think what happens as lambda is getting smaller. So what's happening is lambda is getting smaller. What that means is the lambda of t reduces. So that means that the negative energy, this is a double negative coming up, so just watch out for that. So the negative energy associated with the domain wall between normal and a superconductor is going to become less negative. So now what happens as a consequence of this? So there's two things that could happen. So the first consequence is that as I go towards zero temperature, again, along this line that we have, that I have up here in gray, as t goes to zero, the energy of the wall, of the domain wall, is still negative. And the vortex state persists. So you always stay in the vortex state. So that's a logically allowed possibility. The second possibility that can happen is that E wall T is not negative enough for the vortex state to be thermodynamically stable. So then there'll be a TC of H, and I'm going to call that TC1 of H, where the system can reduce the free energy by completely expelling magnetic field. Just like the type 1 superconductor. So that's what could happen. So if that did happen, then what would that look like? Well, that would then say that we have, let's so let's add another line over here. So that says as I go along here, somewhere there's a value of TC1, which that's what I called it, where, and that's going to depend on what my external magnetic field is, so it'll be a function of H, so where as I go below that, then I end up in the Meissner phase. And so if I were to draw that, that would look something like this. And this line would be HC1 of T, and this phase here would be the Meissner phase, and this phase here would be the Abrikosov phase. And and we can ask, well, what is HC1? That's what I'm going to do on the next blackboard. So how do we calculate HC1? So let's think of it like this. Let me call epsilon of t. Let me define that to be the free energy per unit length of a vortex line. This is a quantum vortex line with a normal core and magnetic field going through that core. So now if I'm at HC1 plus, just slightly above HC1, I'll have one vortex in the system. If I'm slightly below HC1, so let's call that HC1 minus, then there's no vortices in the system. I'm now in the Meissner phase. So what that means then is that at H equals HC1, at that temperature T, the Gibbs free energy with no vortices and one vortex are the same. So we can say that the Gibbs free energy of the superconducting state with no flux going through it is equal to the Gibbs free energy of the system with one vortex. And I'm not going to go. In previous years, I've given this as an exercise for students to work out. I'm not going to do that this year. So let me just tell you the result. A detailed calculation shows that HC1 of t is equal to 4 pi epsilon of t over phi naught, and epsilon of t is equal to phi naught over 4 pi lambda of t all squared times the log of lambda of t over xi of t. Okay, so this is analogous exactly to what happens in the rotating superfluid, where there's a rotation rate where you have no quantum vortices in the system, and then as I increase the rotation rate, I now start to get one vortex in the system. And so this is the exact analog. And just as a comment about this formula, there's something you can notice about it straight away. Note that the energy is proportional to the flux squared. Okay, that's the first bracket in it. And so you can already guess that the system will minimize its energy by making singly charged flux tubes. When I say singly charged, I mean with quantum number n equals equal to, not quantum number, but with number n equals to 1, rather than the lowest possible value that you would have for the topological charge. Not multiples of the Fluxoid quantum. Okay, so we've got a bit of a picture now about the magnetic phase diagram, and what I would like to do now is talk about the topological consequences of that for superconductors. So I want to talk now about Fluxoid quantization. So what we're going to do in this section is we want to expose the topological origins of a Fluxoid quantization. And what we're going to do is very analogous to what we did with superfluids. Analogous to superfluids in a annulus geometry. So this is going to again be the interplay between geometry and topologically charged currents and so on. Okay, so let's get right to it. With the theory. So I want to imagine now that I have a superconductor, which is some annulus like this. So this is a superconductor, and then of course in the middle there's nothing, so we'll consider that to be normal, and we'll consider a trajectory, a curve that goes through the superconductor. Oh, that wasn't very good. Let's try it again. So we have a curve that goes through the superconductor like so, and we're going to assume that there is a magnetic flux. There's a magnetic field coming up through the paper like that. Okay, so let's remind ourselves what the current was in Ginsburg-Landau theory. So in Ginsburg-Landau theory, the current that you get when you have a superconductor in the presence of a vector potential was the formula, this formula that I wrote down last time. So it's this plus its complex conjugate. So that's the formula for the current. And if I write down the psi is equal to ns times a phase, like so, then what I get is that J is equal to E ns over 2m h bar grad gamma minus 2e over c times the vector potential A. And this is a very important formula. And I want to just remind you what it means. So this part over here This part over here is exactly what we saw in superfluid. There we saw that V was something or other, h bar over 2n or something times the gradient of the gamma in a superfluid. But then we've got this extra term. This extra term comes from the magnetic field. And this extra term makes all the difference. So we're going to do the same kind of trick that we did before. We're going to consider this formula and integrate it around the curve. So let's now integrate around the curve C, just like we did in the superfluid case in order to get the circulation. So we integrate around the curve C. And so that's going to give us the following. Integral of J, oops, let me start again. First of all, I'm going to write down my integral. On the curve of J dotted with dr, and we can just do this in our heads. This is going to be ns times E over 2n. And then we've got two terms now. One is just the integral around the curve of the gradient of the phase, which is exactly what we had before. But now we have another term, which is 2e over c times the integral around the curve of a dotted with dr, like so. And I think you can probably see where this is going, because the last term there is the same as the flux using Stokes' theorem. So here's the flux. So that's defined to be the line integral around the curve C, A dot dr, and then that is the surface integral of H dotted with ds by Stokes' theorem. So here I have a curve like that. So here is a curve C, and then on top of that curve C, I have some surface like so, which is bound by the curve C, and so this thing here is of course the flux. So now I'm going to define the fluxoid. So that I'm going to call phi prime, and that's equal to h bar c over 2e, the line integral of grad gamma dot dr, and so now putting all of these things together, we can see that phi prime, the fluxoid, is equal to the flux phi, and then there's this first term, which is the term m c over ns e squared the current dotted with dr, and this prefactor, you'll notice, is the same thing as the electromagnetic penetration depth. So I can write this as 4 pi over c lambda penetration depth squared times the integral of j dotted with dr. Okay, so that's all of that is exact. And now we're going to do the same thing that we did with superfluids. We know that the wave function of the condensate is single valued. And so what that means is that when I integrate rad gamma dotted with dr around a curve, that's equal to the total change in phase is equal to the total change of phase, which must be a multiple of 2 pi n, where n can be 0, 1, 2, and so on and so forth. And so now you can see that because the condensate is single valued, that means that the fluxoid is the thing that is quantized, not the flux. And it's quantized in units of the flux quantum. Phi prime is equal to h bar c over 2e times 2 pi n, which is equal to n times phi naught. So that's the exact formula. So why do people talk about the quantization of flux? Well, we talk about the quantization of flux because usually we take the surface, not the surface, the contour, well inside the superconductor. And so that means then there's no field there, and therefore J is equal to 0. And so then the flux and the fluxoid are the same, and so that's why people often talk about the flux being the thing that is quantized. All right, well, I want to end this lecture by talking about the little Parkes experiment. Okay, so this is the first thing, just quantization. Now I want to show you what is the experimental evidence for this. So this is a very clever experiment to show that it is the fluxoid that is quantized. So what was the technique? So what they did was they measured the variation of Tc with an external magnetic field in a thin superconducting shell. So let me try to sketch the system. So imagine I've got a cylinder, not quite as wobbly as my cylinder, like so, and then it's a shell. So and here is the vacuum. Doesn't look very thin the way I've drawn it, but it's supposed to be. Okay. So this is the shell, and it's meant to have a current which is going around like so. And then what we're going to have is a magnetic field going, of course, up through the axis, like so. We're going to assume that the shell has a thickness d, and the radius of the shell is r, and we're going to assume that r is, of course, much larger than d. Okay, so what did they do? So how did they make this shell? Well, never mind. So what we're going to measure is Tc as a function of h, and h is the field inside the cylinder. So the flux is just pi r squared times h. So let's suppose I write the current as a number of superconducting electrons times the charge that they carry times their velocity. So what we know is that we know that phi prime is supposed to be equal to in units of the flux quantum. And so the velocity is then just given by h bar over 2mr times n minus the flux over the flux quantum. So that just comes from the formula for the current that we wrote down before. So we've defined a velocity from the current and from the flux quantum. Okay, so this is a bit complicated. So let me tell you where the superfluid velocity is coming in here. So just to remind you that the way I want to think about this is I want to think about the superconducting free energy per unit volume. Let me write this as so this is the normal one, and then plus the magnitude of the superconducting order parameter times alpha plus beta psi squared, and then the gradient term is just given by the kinetic energy of the superfluid. So we'll call that a half mv squared, like so, and then we have the kinetic energy, the magnetic field energy, h squared over 8 pi. Okay, so that's how I can think about the circulating current of superfluid, the charged superfluid in this magnetic field. Now, here is the logic, and this I usually have to explain this twice because it is a bit subtle. Okay, so what we're going to do is we're going to choose some field H, and once we've chosen that field H, that tells us exactly what the flux is. Okay, so what values of the velocity field can you have of the superfluid velocity? So there's only allowed values given by quantization. Allowed values of Vs from the quantization condition. So like so. So basically, then what's going to happen is that the system is going to minimize the energy of the current, the kinetic energy of the superfluid component, the charged superfluid. So we're going to minimize the energy by choosing the value of n that minimizes Vs. And this is the subtle part. So that will, this value of n has the lowest energy in the superconducting state. And so it's going to be more thermodynamically stable than other values of n, or other states with different values of n. Okay, if it's more thermodynamically stable, then that means it will have the highest TC. When n is chosen. To minimize Vs. Okay, so let me draw the diagram that goes along with this, and then you'll start to see what I'm talking about. So here is the value of Vs, and on the horizontal axis, I'm going to draw the flux, which is really the magnetic field, normalized in units of phi naught. And so Vs, as you can see from forming a star over here, is linearly proportional to n. So it'll go, let's suppose we're at the origin of this. So this is Vs. So let's have a look at what we expect to happen. So the Vs is linearly proportional to the flux. But once it gets to this value here, it's better for it to flip back down to this value and then go up like that, and so on. And the same thing over here. So what you get then is that this state over here is n is equal to 0. This one over here is n is equal to 1. This one over here is n is equal to -1, and so on. And so this must be the form of Vs. And so and you can see that Vs is a periodic function in phi and thus in h. So I can calculate what Tc of H is by minimizing the free energy with respect to the order parameter. And so that gives me that psi squared is equal to minus alpha minus m bs squared over 2 divided by 1 over beta, just minimizing this function form over here. And this has to be true. Of course, we need that psi squared has to be greater than 0. And so that means that alpha minus alpha is greater than or equal to mv squared over 2. And of course, alpha is just the transition temperature. So this is minus alpha, which is a function of Tc as a function of H, has to equal mvs squared over 2. And alpha is equal to some constant, alpha naught, times T minus Tc over Tc. And so what that then gives you is that Tc minus Tc of H over Tc is equal to m bs squared over 2 alpha naught. And so what you're going to end up with is a periodic variation of the critical temperature. So because it goes as mv squared, what it's going to look like is this. So here is the magnetic field, or the flux. Now I'm going to plot Tc minus Tc of H over Tc. So when I don't have an H, I just mean that H is equal to 0. And so because that goes as mv squared and v goes like is linear, then what this is going to look like is a series of parabolas like this. And so this is equal to 0, this is equal to 1, this is equal to minus 1, and so on and so forth. And what that means is that if you measured the resistance at fixed temperature, as a function of H at fixed T, it should be periodic with a period of the Fluxoid quantum. And that's exactly what they observed. So so I want to go back and make a comment about this equation, which is doubly starred here, because I think when I was explaining it, I think I skated over it a little bit too quickly, and I want to end by just going back over that. So let's just recap why we get that Vs is equal to h bar over 2mr times n minus 5 over 5 naught. So let me try to explain that one more time. So we start off with the flux as just being pi r squared h, and J current is equal to number of superconducting electrons, as it were, times their charge, times a super current velocity field. So what we know then is that phi prime is equal to, if that's the fluxoid, is mc over ns e squared times j times 2 pi r. That's doing the line integral. That's doing the line integral over here. Okay. So phi is equal to that plus phi naught, and that has to equal n phi naught. And so therefore j times 2 pi r is equal to n minus phi over phi naught times phi naught ns e squared over mc. And then I can simply rearrange this, and this gives me that j is equal to h bar over 2m r times nse into n minus phi over phi naught. So that's how I got this formula for the velocity. Okay, well, I think that's where I'm going to stop for today. We've gone on long enough. Next time we will finish our discussion of superconductors by talking about the Josephson effects.